Good. So now we have a solid basis of texture, X-ray focusing. So now we can actually think about doing experiments. And that's what my talk is going to be about. How to do the experiment, which are the pitfalls that I encountered. It's very based on my experience, so I also want to take 30 seconds to introduce myself for those that don't know me. I'm Tilman. I'm working at the Institut Fresnel in the comics team. We are a team that is on the one hand developing techniques to look at crystalline properties in 2D and 3D. So a part of us is doing a lot of brachytechography, polarization microscopy. I do the texture tomography part. And then we try to use that to actually look at biomineralization processes. So we combine the two expertises. We are unfortunately not on this beautiful campus. We are up in the north, but it's way easier to get there. I also want to thank my team for everything they've been doing with me for the last couple of years. A lot of what I'm talking about is actually the experience that we gained together. I also want you, if you have questions that come up during the talk, points you strongly not agree with me, bring it up and we can discuss it. I think this is more fun if it's interactive than me just rambling about experiments. What I want to discuss now is basically what are the considerations before we do an experiment? What do we need to do in terms of getting a good sample? What is a good sample? For texture tomography and tensor tomography, they are kind of similar on most points. How do we measure? What is the sampling required? And how do we reconstruct our data? So before you even think about doing an experiment, it's important to have a scientific questions. I mean, I know that I'm preaching to the choir here, but it's really a lot better if you think your experiment through before going out on a fishing expedition, hoping to find something. Does it need a synchrotron? And what do you actually want to do with your data afterwards? I'm guilty of that myself. There's a couple of experiments that took me 10 years to analyze because I didn't know how to analyze my data. And we finally published it this year. My presenter is really not great. First of all, I mean, just to get the terminology all straight in our minds, I mean, I'm going to talk a lot about hierarchical imaging. What I mean with this is that we basically have a certain field of view, which is kind of how large do we scan the sample. We have a certain kind of step size resolution that comes from the size of the X-ray beam. That's kind of our real space resolution. And then we are collecting diffraction patterns. And from these, we either extract crystal structure information from the wax regime or nanostructure information from the SACs. And that's kind of our reciprocal space resolution that comes into this. And just, yeah, if you could just set it up. And what's important to keep in mind before we do this kind of orientation-sensitive diffraction experiments is figuring out where our scattering signal actually comes from. Because, I mean, if we take my favorite example of a mineralized collagen fibril, yes, that is a lot better. Thank you, Moritz. If we take my favorite example of a mineralized collagen fibril, and we look at the diffraction pattern, there's a lot of information. So here you don't see, but here you actually see the collagen reflections. Yeah, I mean, it was on 30 seconds ago. Yes. So here, if we look at this signal, that just comes from the collagen fibrils. We also have the signal from the mineral at the same time. And then if we look further, we also have the diffraction signal from the crystalline portion of the mineral. And all this is kind of meshed together in the diffraction pattern. So what I want to say is it's important to know where your signal comes from, to have an idea what you're reconstructing afterwards. Again, how robust is your design of experiments? How many parameters do you have that you want to vary? How many samples do you have? And is it realistic to do that in a couple of days of synchrotron beam time? I mean, it's unreasonable to ask for 5 weeks of beam time just because your design of experiment is humongous. This is just something to consider before you actually think about it. Do you have preliminary data? Do you know how your sample is scattering, which energy, which Q space? I mean, it's very general considerations, but I think it's good to have it written down for this tutorial. And again, is it a 3D experiment? Is it really something where you need the 3D capabilities, or is it something that you can tackle with the 2D experiments? Because they are really a lot easier. Then, do we need a synchrotron? Of course, beautiful beam lines with small, brilliant beams, super coherent 4th generation synchrotron sources, multimodal detection, way too much flux for your own good. We can tune the energies to whichever absorption edge we want to look at. So it's amazing, obviously. I mean, we're all here because we like that kind of stuff. The downsides, of course, is that it's an extremely long process. I mean, writing a proposal, getting your beam time, that's easily half a year before you've even done your experiments. There is a substantial effort to prepare your experiment. I mean, I cannot overstate how much pain it is to prepare an experiment properly. One personal note for me is really just apply for the time that you need and only apply for one synchrotron at a time. It's really, I consider that practice if I see the same proposal in 2 different review panels. It's really a waste of other people's beam time. Because you usually get more beam time than you actually need. Some things to consider: are you able to handle your data? Are you able to analyze your data? Do you have the right codes? Do you need collaborations? If you need them, ask them before you write the proposal and not just pop up in someone's mailbox with I have 20 terabytes of data, I need your help to analyze it. And talk to your local friendly beamline scientist to see if your idea is actually feasible. They're very accommodating, but you need to talk with them before. Good. After my initial rant, let's get down to tensor and texture tomography. Mostly focusing really here on the experimental part. There's a couple of different flavors of what we now these next couple of days going to group into this orientation-sensitive diffraction techniques. What I would usually call the peakiness of your signal. So if you look at the diffraction pattern, do we have like these nice single Bragg peaks popping up? Do we have a couple of them, which makes them a 3D XRD experiment, for instance? Or can we directly image them with these amazing dark field microscopy techniques? Can we single out a single Bragg peak and really look at it in detail with 3D Bragg tachography, Bragg CDI experiments, or this the new kid on the block, the linear dichroism tomography? Or then if the peakiness scale gets a bit broader, we have texture tomography, we have SAX tensor tomography for the nanostructural part of it. And it's not orientation sensitive, but it's a very valuable tool. In the toolbox too is XRD-CT to look at average crystalline properties. So it's really important to pick the right set of technique for what you want to do, and then design your experiment accordingly. Basically, how many samples do you need? Can you combine 2D and 3D experiments together to have more coverage of your experiment? What do you need in terms of field of view and spatial resolution? Doing a higher spatial resolution experiment always means you have less context in your sample. If I take this example here, where we had a degrading magnesium implant in a rat femur, and we wanted to understand what's going on around it. You really need to have a certain size of your sample to understand the science of it. And yeah, I mean, my personal experience is that you can usually, if everything goes fast, you can aim at a factor between field of view and spatial resolution of 200 and still be in a 3 to 5 hours per sample regime. The ideal sample is cylindrical, free floating in air, nothing around it, and you can just easily rotate it. In practice, we need sample support. What tends to work well for us if we need to cut the sample afterwards is PMMA. I mean, here I'm talking about a 50 micron sample, something like this, just to give you an idea for high resolution imaging. So we have these PMMA needles where you can put your sample and then you can get it smaller, but I'll talk about that later. If you have a small sample that you just need to stick on somewhere, glass needles are amazing because they don't give you a lot of background, but you don't want to start preparing a sample while it's on a glass needle. And if your sample is a bit larger, more permissive, steel needles are an excellent way of mounting your samples if your sample is a bit more chubby and bulky. What do you also want from your sample? You want it, I say isolated scattering. So basically you don't want to have scattering from your sample support. So that's a nice sample. The bad thing about the sample, a couple of scans later, the sample exploded in our face and I think this is 2 scans before, and then the sample just erupted and left us with a very nice image of a glass needle. And is also the more cylindrical, the better. These kind of weird, funky shapes are a nightmare to align, and the alignment step is really a crucial one in the reconstruction process. So the more cylindrical you get to your sample, the better for you in the future. How to get there? I mean, the easy way for millimeter-sized samples, you just cut them with a very poor use of the space. With these diamond cutoff wheels, you can cut millimeter-sized samples, no problems. The problem is that you're not really selective to where you're cutting. If it comes to this 100 micron scale samples, you have these tomolathes. Henrik wrote a nice review about it last year. They are great for getting a very round sample, or very cylindrical samples. Choosing the region of interest is more tricky there because you need to be on the center of rotation with that before you do the cutting. So that's a bit finicky. And if you really want to get localized small samples, you have this focused ion beams and laser ablation techniques. It just gets very painful. I mean that's my takeaway message for this slide is that that's a pyramid of pain. I mean, here this is something you can do in an afternoon. This is something you can do in a couple of days. This takes weeks. I mean, we had an experiment with my PhD student Momo, where I think we spent 3 months on 4 samples. And you don't want to know how much money we spend on this. It was worth it in the end, but it's really cost scales very unfavorably with the size. So really think about your experiment before and how you want to prepare your samples, because the good news is once you're here, you've done 80% of your work, in my opinion. Getting the right samples is really most of the work, in my opinion, for these kind of techniques. That's just these famous samples from Momo. We needed to cut them out. The problem is that we need to be localized on this structure, so we need to cut them into a block. We need to figure out how the block looks like with this lab CT. It's painful. It's painful, but it's worth it. This is how the sample looked in the end. I mean, Momo has them on his poster. Take a look there. It was absolutely worth it, but it takes a lot of time. that you need to factor in before you do your experiment. Once you're at the beamline, once you start, keep a detailed logbook. I mean, in the preparation of this workshop, I was actually looking at the earliest paper about X-ray diffraction from Friedrich, Knipping, and Lauer, and they make a note about the sample detector distance that they had trouble determining it. So it's an old problem. Keep a good logbook, sketch out the geometry. Figure out in which way a motor moves. Marianne is laughing because I think the first experiment at ID13, it took us what? A month, 2 months to figure out all the crazy ways.
We considered to put it as optimization parameters.
Yes, yes, yes. I mean, you can save yourself a lot of time by having a good sketch. Try to have an object that you can scan, that you actually know the shape macroscopically, so you see how it moves. I know that it sounds super stupid, but super stupid can take a couple of weeks to figure out, at least for me. Calibrate your setup again, and then when you set up your detector...
Can I make a note?
Oh, absolutely.
We have done it now at several beam times, and now we always, when we go somewhere, we make this like one measurement of like a knot, depending on if it's wax or wax hair works well, or I think some metal knots we also used, because kind of this real space, reciprocal space, flipping thing, it's terrible, and it's really worth to have this as a test sample.
Yes, thank you, Marianne. But yeah, that's exactly it. I mean, I cannot overstress how important keeping a good logbook is, and I'm not good at keeping logbooks myself. Also, make sure that the signal you're interested in is not ending up in a detector gap. Just a little personal experience here too. Air gaps are really bad. I mean, as much as I love your multi-layer Lauer lenses, but in my mind, they give you way too much working distance. So really try to get your, I mean, I'm not kidding. It's really about getting the background on. Every air scattering photon that you have in your detector image decreases your signal to noise. You don't need that. Try to get everything as close together as possible. Not too close, but too close for comfort. And then once you start your experiment, it basically comes down to your sample is somewhere, the center of rotation of your experiment is somewhere else, and you need to make these two coincide as good as you can. You have some kind of sinusoidal offset between these two. If you're lucky, your sample is large. I mean, the problem here is that you basically need to scan everything sitting on top of your scanning stages. So that means the correction for the center of rotation that needs to be done on this level. So if you have a big diffractometer, this is no problem. But if you turn into the nanobeam side of life, having centering stages on top of these two rotational tilt stages starts to become tricky. So yeah, you're lucky if you have this. That's great. That's good for micron-sized resolution or stepping. If not, you have this inverse centering problems that are a bit difficult to work out at the beginning, but once you know how to do it, they kind of work well. The idea is basically that you figure out, I don't figure this out, where your sample is before, and then you apply these corrections during your scan. A word about transmission detection. It's really nice to have transmission data of your sample. It's really, really nice to have transmission. For the SAX case, it's kind of easier because you can afford to have a large beam stop, which is also a photodiode. That works nice. You have some high energy limits. You have some dynamic range considerations, at least, that you need to have before you start your experiment. Semi-transparent beam stops, basically a beam stop that is just an absorber that is thick enough that you don't kill your X-ray detector afterwards. They are super nice in theory. As soon as you have higher harmonic problems or scattering from the beam stop or a detector that doesn't have a super stable flat field, this can really turn into a problem. So they are great if they're properly set up, but the pain you have to get a beam stop that does exactly your attenuation is significant. What we have been working on the last year was getting basically an avalanche photodiode and a special beam stop that has a fluorescence target embedded. That seems to work really well. So you basically have the fluorescence of the beam stop as your counter. That works well, that can go fast, and it's reasonably cheap compared to this hand-tailored solutions here. It's not as accurate as a photodiode beam stop. I don't yet know where the problem is, but just to put that out, the transmission detection is also something to consider before you do your experiment. Why does transmission matter at all? First, we need to have some proper scaling, not only of the transmitted, but also of the diffracted beam. What I mean with this is if you look at these two beam paths of the diffracted beam, the diffraction that comes out at the top of your sample is a lot less attenuated compared to the one that is going through the bulk of your sample. That creates some anisotropy in the diffraction pattern that is not necessarily because of your sample being anisotropic. Ways out are, of course, as always, make your sample small, go to higher energies, or you just correct for it, which becomes computationally expensive if you do texture tomography. Radiation damage is a very important consideration. Henrik is smiling. That's how you calculate your dose. And these are the handles that you have actually. So one is going to higher energies, playing the mass attenuation card. The other one is going really, really fast. Really, really fast. I mean, try to get your detector as fast as it can run, and you will see that you still want it to run faster. That's also why it's important to optimize your setup, because you really want to be able to get to this 2 millisecond sweet spot. That helps a lot. Just to remark, ask that your fast shutter is properly working. Some beamlines don't consider fast shutters as a really important piece of equipment. Radiation damage is really complex. So you really need to sit down for every sample system, for every beamline, for every energy, and figure out what is the photon budget that you have. What we do, one way of doing it is you sit in one point, you do a time scan, you look at the decay properties, you decide on where you think the decay becomes something that impacts your orientation signal. Again, here, think about what you want to do with your data. What do you want to take out of your data? Where does radiation damage interfere with this information? And then try to stay away. And stay away for the whole tomogram, of course. It goes without saying. Yeah, so the 50% damage onset is something like a historical criterion that people are using. One last note about sample. I know, I know. If you have this nice little pillar here, you need to make sure that your sample is fully in the field of view at all times. Otherwise, you really have a hard time in the alignment step. And that also means that, for instance, if this whole sample is sculpted out of a bigger sample here at the bottom, as soon as you start tilting it, you will get what I call rogue scattering. That doesn't really come from the sample, but from the sample support. This, again, is going to give you a hard time later when you reconstruct your tomogram. So really this freestanding, isolated, scattering a pig sample floating in thin air is really something you would like to have here. When it comes to sampling, so now we have our sample, everything is nice and tidy. How many angles do you take? I mean, this is always the 2 in the morning question. How do we actually distribute our angles? If you look at the classic Shannon-Nyquist for scalar tomography, you should have this 1.7 over 180 degrees. The time constraint CT is usually, how much beam time do we have left? And you try to somehow get yourself to 1 for K. I didn't really find a good description for the tensor tomography experiments. I know that with Marianne we discussed up to 6. It really depends. In my experience for the samples we have been working on with Moritz the last couple of years, K can go extremely low, but the tilting of the sample actually matters a lot. What I mean by this, so here we have this famous helix that you're all going to reconstruct in the afternoon. It's about a 20 micron object. We had a 500 nanometer voxels, so you want to have something like 40 projections. I know that this is kind of a very nice case. If we took a full data set, 256 projections, reconstructed that, and then we downsampled our data set, and it turns out that 41 projections, so here that's the orientation difference, 41 projections equally sampled over this orientation space gives you a very decent reconstruction, but as soon as you restrict yourself to just the rotation without any extra tilts, you start to get these deviations, especially in regions that have a fairly broad texture. Again, this is sample dependent. This is crystal structure. I think I have this. Yeah, it's sample structure. It's crystal structure dependent. The diabolic thing here is the codes always give you a reconstruction. You have no way of knowing if you're looking at rubbish or if this is your real sample. So I would try to stay cautious. But I think we should discuss in this workshop also how we can get...
Is it not enough if you, from your solution, predict your patterns to gain trust?
It's one way of doing it. If you're able to have a forward model of your sample, of course. If you're able to put your scientific question, is this misorientation, for instance, something that is real, or is this something that comes out of my reconstruction? If you're able to model it, of course. I mean, that's the gold standard of doing it. Yeah, then there comes this moment when you look at your hard drives during the experiment and you realize you have done the first 20 terabytes. Think about your data transfer. Think about the 2D data integration that we at least need for our code. Do as much online as possible. Try to include the Beamline scientists in the discussion early on so they can set up scripts for you. Also, in the interest of future users. I mean, it's great if that works for you, but if you want to build a community and have these experiments easily, we kind of need to agree on certain ways of doing it at a certain Beamline at least. There's also a lot of computing resources available at synchrotrons that we should tap into. Not everybody needs to buy a 50K computer to do their reconstructions. One way, of course, would be going to the Dectris cloud. Another one would be use the computing resources that we have available. I mean, I cannot overstress that having these kind of pipelines kind of unified will make it easier for us as a community. When it comes to pretty pictures, we actually want to have scientific results. So there's a step of exploiting the data, try to exploit the statistics that we have by having all these per voxel statistics within our sample. We can try to link with all the other modalities that we can record at the same time, fluorescence signal, the extra 2D experiments that we did, XRD CT. Because it's just difficult. I mean, if I look at, this is a paper I did a couple of years ago. If you look at this forest of glyphs, there is not too much you can tell here. Even if you try to slice it into a 2D problem, it becomes clearer. But really segmenting it out and then plotting all these parameters as a function of distance made the whole scientific story so much clearer than looking at this glyph forest. So there's really, you need to work on how to break down your data. When it comes to publication, of course, report as much as possible, share your code as much as reasonable, and also add your Beamline scientists or acknowledge them at least. It's really important for the synchrotrons to get that back. I mean, they put all this work and the beamlines you're working on, that's 10, 20, 30 years of work that has been going, and you kind of profit from all that. So the bare minimum we can do is really give them the publications back. Us as a community, I would like to create a mailing list. So please subscribe if you're interested in keeping up with that. We're also recording these tutorials, so they're available for you to work through afterwards. And with this, I think I come to my last ranting take-home messages. Make a good design of your experiment. The sample preparation is most of the work. Document well, and be cautious with radiation damage. And one more thing for a good experiment. You need to have your lucky socks with you. I mean, that's something we do in my group now. We have our lucky socks. All the experiments we did with them were great. The one we did without them was a total shit show. You need to have these kind of superstitions to, you know, take the edge of a 2 in the morning night shift, this kind of stuff. Yeah, so thank you. And